Okay, our next speaker is Abdou. He's from AIMS Rwanda, right? Go ahead.
Okay, good afternoon. My name is Abdou. I'm a student of Dr. Yan. And I want to present on inevitability of polarization in geometric opinion exchange. It will be a big picture of a paper we have recently put on archive with Julia Baligach, Mashan Klimroth, Lucas Rinse, and Olga Sheftelowicz from these schools. And it discusses opinion dynamics. In societies in general, well, not in general, but in some societies, we observe many different, how should I put it? We observe a phenomenon called polarization. It is something that happens when people form clusters of opposite opinions. And it is a phenomenon of interest to social scientists and computer scientists, among others. Opinion dynamics has been studied more generally by economists. And well, let me just start by introducing how they try to model this with mathematics. In general, we start with some agents, say n agents, and some topics. And on each topic, you assign to each agent some opinion. So that opinion is simply a real number. That is why I show here a vector. Let's say agent I, you give it very favorable opinion on this topic here, which is negative. When it is favorable, it is positive, something like that. So we just have vectors for opinions for individuals. Okay. And what do we do with that? We define some rules by which the individuals interact. These rules simply means that you start with some configuration of opinions in the society, and based on interaction, conversation with each other, or influence of the media, for example, state laws, they update those opinions according to these rules. And what we are interested in most of the time is what is going to happen if we wait long enough. Are the people in the society going to reach consensus? On Facebook, probably not. And is it possible to spread misinformation? Can some malevolent agent somehow play the system or things like that? And we're also interested in the kind of network structures in which some phenomenon develop, in which these things can happen or may not happen. There have been some interesting results from mainly economists. Probably the most popular model is what is called the de Groot model. And this model is basically the straightforward models you can think of. You start with some opinions, some belief about the world, and you average the beliefs of the people around you. So conversation with people in your social network, you average their beliefs. And this is a weighted average because you give some weight to the trust that you have in each people. And these guys showed that in such a model, you will tend to reach consensus if you wait long enough. Another interesting result is Oman's agreement theorem. That is a theorem that says that if you assume that the agents, the rules according to which they update their opinions is basically the base rules, so completely rational agents, then they will also tend to achieve consensus. But we know that sometimes that is not what happens, which is what I was talking about initially. We're interested in the phenomenon of polarization. And one striking example of this is probably, currently is probably the political landscape in the US with the left and the right very divided. This is a graph of the interest of people on Facebook, for example, right after the 2016 election. And you can see that there's barely any connection between the two groups, really. They have different interests and do not interact much with each other. To illustrate this further, you see a map of how the polarization phenomenon has been emerging over the last 2 decades in the US. Assume by now it is a little worse. Anyway, this issue of polarization, they study it from mainly 2 aspects. One is the fact that people end up in opposite clusters that we call issue radicalization. And another interesting fact is the fact that sometimes people's opinion on different topics tend to align. I mean, a priori, you wouldn't expect that on topics like, this is a very hot one, Palestine-Israel conflict, climate change, immigration, gun laws, you wouldn't expect a correlation between opinions on these topics. Like the same people with some opinions on this have the same opinions on the other. That is something that is unexpected. That is the other aspect of polarization. So what we are interested in doing is to find some reasonable, simple model of the update rule, some reasonable update rule that can show how these phenomena can emerge. And the update rule we use is inspired by what social scientists called biased assimilation. That is basically the tendency to more or less like to hear what you believe, and you dislike to hear what you disagree with, basically. When you discuss with someone with a similar opinion, you tend to easily accept what they are saying, and when it is an opposite view, you tend to reject it a little more strongly sometimes. This does not always happen, but it has been studied in social science literature. Okay, so how do we define our model? We start with an initial configuration of opinions, so with n vectors in some d-dimensional space. These vectors, we make them unit vectors, so they are on the unit hypersphere. And you can see this as a little bit giving them some budget of attention, I would say, so that if you are very involved on some topics, you don't have enough time to be involved on some other topics, so that is the intuition behind that. And what we do, at every time steps, we pick simply a random pair according to some distribution, and we let those pair of agents interact with each other. In particular, we let one agent influence the other, and we update the opinion of the other. In this case, for example, at time t, you have agent I with the opinion UIT and J with opinion UJT. And in order to find the new opinion of UI, you obey this following rule. This is just a normalization. As I said, we are on the sphere. And the rule is basically that you add to your opinion a little bit of the opinion of the other party after the interaction with them. What we are going to be interested in is how, depending on which function we choose here, this is a function of the correlation between the opinion. As I was saying, we want to include the idea of bias assimilation. So if you are close to someone, after an interaction, you will tend to get a little closer to them. If you are far away from them, you will tend to get a little further away from them. That is why this F is a function of the correlation between them. And what we want to study is if you wait long enough, do we get all the opinions to converge to more or less one vector and exactly the opposite vector. And in order to encode this idea of bias assimilation, that I was saying, we simply set that this the sign of S is preserved after the function. I mean, sign of f of S is cosine of S. And how would this display in the model? For example, if you have U and J positively correlated, then you are adding to I. If you have I and J, UI and UJ positively correlated, then you add to UI just a positive portion of UJ. So you will get closer to them and the correlation will increase. If initially you were negatively correlated, then you will add a negative portion of it. And so you will get further away from it. You will still be a little more negatively correlated. As you can see on this graph, this is initial UI, UJ. They are negatively correlated. So after the interaction, after you add a little bit of minus UJ to this, you get a new vector that is further away from UJ. Okay, and this model initially, it was proposed by my supervisor and colleagues, and they initially worked on the case where people are not interacting with each other, but they are under the influence of some external agent like media, as I was saying. And the work was extended by some of these guys. Anyway, what we really add to this is the fact that the opinions, the interaction are between the pairs, are between the agents. And the result that we get from this is that in general, the condition of bias assimilation, the condition of sine of f of s equals sine of s, and the fact that this is a geometric rule, you have all components of the vector interacting at every time because it is a function of the correlation that is sufficient to get polarization almost surely if you wait long enough. This theorem for 2 dimensions states that under the following conditions, you will get polarization. First, the starting configuration should not be separable, and what we mean by separable here is that it cannot be separated in orthogonal subspaces. And the idea here is that from the whole sign concerning the sign, you have that when opinions are orthogonal, there will be no interaction because then the function is 0 and nothing will happen. That's just a technical part here. Then the condition on F, and finally, a condition on the distribution from which you are picking them. We need that at least the distribution be such that every interaction has at least some non-zero probability of occurring. So under these 3 conditions, we can show polarization almost surely. And the case for higher dimension is a little bit different. Well, it is more or less the same thing, but because of technicalities regarding this case, this orthogonal case also, it is a little less general. But before I get to that, let me quickly give an overview of the argument for the 2-dimensional case. The most important part is showing that the opinions, the configuration of opinions becomes strictly converse. What we call strictly converse, you can read it from the definition here. It means that up to flipping some of the opinions, you can get all of them in some sort of cone that has width of less than 90 degrees. And the idea is that intuitively, strictly converse opinions will polarize because they are already inside the converse cone. The interactions will, it's not very obvious, but it is intuitive, I would say. Okay, and in the 2-dimensional case, what happens? The difficulty is mainly when the opinions start from a configuration that is close to the orthogonal case, which is difficult. But in that case, we can show that there is a constant probability that the opinions will end up in a convex cone. For example, this is here assume that all the opinions are within these two blue areas. That would mean that they are not strictly convex because you can put all of them inside one quadrant, like less than 90 degrees. But what you can do to make them all strictly convex is just to pick some, let's say these two opinions, and apply each one of them to all the opinion in its cluster until they get above the line. And that is possible in a constant number of steps because the kind of function that we are assuming, when you have an interaction, you can just make opinions always move by some constant distance, I would say. That is why it is possible in a constant number of steps. Anyway, this result that in 2 dimensions, you can get this in a constant number of steps does not work for higher dimension. Actually, we could come up with a counter example for higher dimension. For any k that you take, you can always come up with just 3 opinions in 3 dimensions that would such that the configuration would not be strictly convex after k steps, whatever interaction there is. And to avoid this, the theorems that we have for higher dimension simply state that if configurations that are close to almost orthogonal do not say almost orthogonal forever, then you get polarization almost surely. So indeed, it is only the orthogonal cases that cause problem. So for the subclass of function for which it will almost surely escape the almost separable configuration, then there will be polarization. Or simply, we can avoid that issue about f of s being 0 if you can just bound it away. If you choose functions that are bounded away from zeros, it is sufficient to also get almost sure polarization. And I would say that from our simulations, even when you start from almost orthogonal case or not, you still get polarization in all the simulations that we have tried. Here, for example, I show the polarization process should be read like this. And the update function used is one in which it's just a coefficient multiplied by the correlation. And here we have made it a little stronger when you have similar opinions than when you have opposite opinions, so that when you disagree, you don't disagree more by the same amount as when you agree. And as you can see, if you wait long enough, you get these clusters forming, and then you get the process completely polarized at the end. I will finish by mentioning that this project was inspired by a school that we had in Dortmund last year, a summer school organized by my supervisor and colleagues. And this year also, as he has said, we have another school coming up. So you are invited to share this in your network and apply if interested. Thank you.
Thank you very much, Abdou. Are there questions? Maybe then I ask a question. So what would you say will happen if in this model, instead of, you keep it the same, and then at every step also maybe the opinion is going to move a little bit by some additional Gaussian noise. So you make an interaction according to the rule, and then you add a bit of a Gaussian noise. Like, will that make things harder, easier, different? Yeah.
I would say, well, in that case, well, clearly the orthogonal issues will disappear because you have added a noise, so the opinion will not stay orthogonal forever. But in general, I would say that will mean you'll probably not be completely polarized at the end, because wherever you go, there is still some noise. That's my guess, I would say.
Inspired by Jan's question and your answer, like you still have some noise, and couldn't it be the case that depending on the strength of the noise at the end of the day, you might add up in polarization, in a kind of polarization around some noisy points at the end? And when the noise is quite strong, you might actually see polarization or pseudo-polarization for some time, like a meter-stable situation, which after some potentially very long time destabilizes again, and you start the process essentially from new. This would not really be only Gaussian noise, but I think of like a Poisson point process. You throw some noise after some exponential times, and potentially also large noise, maybe with a power law or something. And you could see some meter-stable stuff maybe.
Yes, I would say the first description that you gave is what I was thinking about. But indeed, if you choose a noise model like what you described, you would probably be jumping from the stable point over and over again.
Thanks.
Okay, we are still on time, so if it's another question, sure.
Good afternoon. I am interested in the summer school event in 12 to 23 August. What is the eligibility criteria for that one?
I believe either a good master's student or a PhD postdoc. That's the, okay.
You have a link, you click on the link, you read the eligibility criteria. But good question, thank you. Okay, thanks again, Abdou.